Welcome to the lesson on work, power, and energy. In this video, we're going to be discussing what work is, how to calculate it, its relationship between work and energy, and how to calculate power. We'll start with work. Work is done on an object whenever a force acts on an object over some displacement. From that definition, we get the equation that you'll see for work on your reference table. W equals F delta R cosine theta. This may look similar, with one exception, to the torque equation that we just got done with in our last unit. And what you see is an F delta R, but this time instead of a sine theta, you see a cosine theta. We'll get to that more in a moment. The units of work are force, newtons, times displacement, meters. But the traditional unit here, the accepted unit for work, is joules. And that's the unit that many of you may recognize from chemistry for energy, and work and energy all have the same units, which is joules. Okay? The keys here for calculating work are that in order for work to be done, there has to be a displacement. So this is the first thing that you need to be aware of if you're asked to calculate work in a problem is, did this object undergo a displacement? For example, and we'll get to this more in our circular motion unit, when an object travels one complete revolution in a circle, it doesn't have a displacement, therefore no work is done. We'd like to pick on track athletes for this, or even you cross-country stars, that when you start from one spot and you finish at that same spot, you have no displacement and you've done no work. So work is a word kind of that has a lot of different connotations depending on the context of the word, but in physics, work is only done when there's a displacement done, when a force is applied over a displacement. The second thing that you need to note here is that the force and the displacement have to be parallel to each other. And this is where that cosine trig function comes in. Let's draw a quick sketch here. We have an object that's going to undergo a displacement R, or you could say delta R, it does not matter. And let's suppose that our force is not parallel to displacement. And our angle here, of course, to the horizontal is theta. Well, in order to calculate work, our force and displacement have to be parallel to each other. In this example, our force is not parallel to our displacement. Therefore, we have to take the component of the force that is parallel to the displacement. This, of course, would be the x component of the force. And how would we calculate that? The x component is adjacent to the angle that forms a right triangle with the force itself, which becomes the hypotenuse. So the x component of that force would be calculated F cosine theta. Just like we talked with torque as well, you can see that F delta R cosine theta is commutative. That means it doesn't matter on the order of the F, the R, and the cosine theta function. Therefore, we could take the cosine theta and attach it to the F, or we could take the cosine theta and attach it to the delta R. And there will be times when you will take a component of a displacement parallel to the force, but more likely you'll be taking a component of a force that is parallel to the displacement. Okay? All right, let's move on to energy. Energy, simply stated, is the ability to do work. And we have specifically we're going to be, in this unit, since we're in mechanics, we're going to be talking about mechanical energy. Okay? 3 forms of mechanical energy. Total mechanical energy is the sum of all kinetic and potential energies that exist in a system. And we have 3 forms of mechanical energy that we'll be investigating this year. We have, scroll a little bit more here, we have kinetic energy, the energy an object possesses because of its movement, and it therefore fits, that our equation for kinetic energy, K, is calculated 1/2 mv squared. So m obviously being the mass, and v being the velocity or speed of the object. Again, note that all forms of energy have units that are in joules. And so kinetic energy would have units in joules. Our next form of mechanical energy that we're going to talk about is gravitational potential energy. There are 2 forms of potential energy that we're going to talk about in our mechanics section. And one of them is gravitational potential energy. Gravitational potential energy is the energy an object possesses due to being at a height above a base level in a gravitational field. The symbol for potential energy in AP physics is a capital U, and we add a subscript little g as our indication that we're talking about gravitational potential energy. Our equation to calculate gravitational potential energy is m, g, and h. So like kinetic energy, you can see that this kind of energy is dependent on the mass. It's also dependent, the gravitational potential energy is also dependent on the acceleration due to gravity, and obviously would change if the acceleration due to gravity changed. Say you went to the moon, for example, or you were at a further distance away from the Earth. And it also depends on that h value, the height above the base level in that gravitational field. The last form that we're going to discuss, and I'm just going to introduce it here in this video, and we'll talk about it more in depth later on, is the elastic potential energy. Elastic potential energy is the potential energy possessed by a system in which it's attached to something that will restore, like a stretched or compressed spring, like a bungee cord, for example. We call that elastic potential energy. We're not going to deal with bungee cords and those kinds of things in here, but we will deal with springs. And that elastic potential energy stored in a spring is calculated by 1/2 K x squared. K stands for the spring constant, and x is the compression or elongation of a spring from its equilibrium position. That's the extent of what we're going to talk about here with this elastic potential energy. I wanted to introduce it as a form of mechanical energy, but we're not going to see this again until we do our simple harmonic motion unit over our February break. Okay. That said, that means that also tells you that we're not going to be addressing elastic potential energy in this particular unit when doing any of our problems. All right, next we have one of the most important physics concepts in the entire unit, in the entire year, and it is the work energy theorem. Simply stated, the work energy theorem states that the work done on an object is equal to that object's change in energy. Okay? We are going to see the work energy theorem applied in all different units now throughout the rest of the year. In this unit, we're going to focus on the total mechanical energy. So we're only going to talk about mechanical energy in this unit. We're not going to talk about electrical potential energy. We're not going to talk about any other kinds of energy at this time, just mechanical energy. So again, reminding you that mechanical energy is the sum of any kinetic and potential energies in the system. So this is saying to you that the work done in an object is equal to the change in the total mechanical energy of that object. Now, the most common application of the work energy theorem in mechanics is that the work done causes a change in the object's kinetic energy. However, we are going to see and do problems in here in our problem set in which you're going to have the work done equal to the object's change in gravitational potential energy. You're going to have problems in which the work done is equal to a change in both the kinetic and gravitational potential energy of the system. Okay, so expect that on the horizon. More to come on this. Lastly, in this video, we're going to talk about power. Another word that has a lot of context in our society, depending on the way in which it's being used. But power in physics is the rate of doing work. The rate of doing anything means that time is going to be in the denominator. So it gives then that the power formula would be work divided by time. An extension of this, if we take the equation for work, which is F delta R cosine theta, and we substitute it in the numerator, and then you can see a further extension of this is that the displacement divided by the time is velocity. So another way to calculate work would be FV cosine theta. The College Board and the AP liked this variation of the power formula. So expect to see this in some manner, either in multiple choice or in the free response section, that the force times the constant speed an object is traveling is a way to calculate power. That'll do it for our introduction. Obviously, much more to come through discussion that we'll have while doing problems in this unit on work, power, and energy.